Lesson 4.2 deals with area. We're going to not go into quite as much detail in 4.2 as your textbook does, because I just don't think it's necessary for what we need to do with area. But we do need to talk about some of the ideas because they're pretty important for us to be able to go on and do other things that are in Chapter 4. We're going to start by talking about sums. This is something that you have probably done back in Algebra 2 when you were in high school, but for most of us it's been quite a while since we were in Algebra 2. So just to make sure that we all understand the notation, we're gonna start with the basics. Sigma notation. This is the Greek letter sigma. Okay, if you're actually looking at your textbook, their sigmas look a lot better than mine will. It's like a capital S in the Greek alphabet. All right, so Greek letter sigma. If we are adding a bunch of things together, okay, term 1 would be a sub 1 plus a sub 2 plus a sub 3 plus, and if we're going to add up a whole bunch of them all the way up to a sub n, rather than have to write out that entire sum the way I just did, we can do shorthand notation using sigma notation. So this sigma indicates that we're going to take a sum of, what are we adding up? We're adding up a sub I. So that little subscript I is like the counter. The I is going to start at number 1, and in the next term it would be 2, and the next term it would be 3. So I, it's called the index, starts at I equal 1, and then the highest number that I gets in this particular sum is n. So the lower bound, the lowest number that your index gets to be, goes below the sigma. The highest number that your index gets to be goes above the sigma. So the lower bound is 1, the upper bound is n. And then a sub I is the notation we use for the ith. Excuse me. Great sneeze on recording. Anyway, so the a sub I is the notation we use for the ith term. So just to make sure that we're comfortable with that, if I gave you a sum from 1 to 10 for I, you need to know that that means take 1 plus 2 plus 3 plus 4 and so on and so on and so on, and there's 8 and there's 9 and there's 10. And I can't extend my page because, alright, now I can extend my page. So if you see, let me change pen color so it's pretty clear we're looking at a different problem. If you see a sum, if I goes from 1 to n, of an expression like this, f of x sub I times delta x, then this could be written, the first term would be f of x sub 1 times delta x, and the second term would be f of x sub 2 gets multiplied by delta x, and so on and so on and so on, and the last term would be f of x sub n times delta x. Now there are some properties of sums that you need to be aware of, specifically, and I think these are going to make a lot of sense to you. Properties, if I can spell the word. If you have a sum from 1 to n of a constant times a sub I, you can pull the constant out in front and just sum the a sub i's. If you have a sum of more than one term, so maybe we've got a sub I either added or subtracted, it won't matter, plus or minus b sub I, you can separate that into two separate sums. So you can look at a sum when I goes from 1 to n for a sub I plus or minus the sum when I goes from 1 to n for the term b sub I. Okay, there are also some sum formulas that you need to just be aware of. I'm not really not gonna ask you to memorize these because I just don't think that's necessary for what we need to do with sums. So sum formulas, just so you have them. And these are in your textbook if you are looking through section 4.2. This first one makes just a lot of sense to me. It seems logical. A sum from 1 to n of some constant. So think about it. We're adding the number c together n times. That can be reduced or simplified to n times c. The sum, if I goes from 1 to n, of just I. So we're saying 1 plus 2 plus 3 and so on, plus 5 plus 6 plus 7 plus blah 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 plus n. That you can find that sum by taking n, multiplying it by n plus 1, and dividing by 2. There's a similar formula for I squared. If we're summing from 1 to n, I squared, you take n, you multiply by n plus 1, you multiply by 2n plus 1. That all gets divided by 6. And you can find the value of your sum without actually having to add all n numbers. And then the last formula, I cubed. Take n and square it, multiply by n plus 1 squared, and divide by 4. Again, you don't have to memorize those, but we're going to need them in a minute, so wanted you to just be aware that those do exist. All right, so here's what we're going to do, working with area. Now I have the right function. This is the graph of the function f of x equals x squared plus 1, and we're looking at it on the interval from 0 to 2. My x scale is actually 1/2, so this is 1/2, there's 1, there's 1.5, so that's 3 halves right there, that's 2. And the y scale is 1, so this is 1, 2, 3, 4, 5. Alright, what we want to do is I want to approximate the area under this curve and above the x-axis. In other words, I want to approximate the area of this space. Now, area formulas we have deal with, rectangles, circles, triangles, trapezoids. We don't really have a formula that will give us an area under a curved surface like this unless we could sort of, if we could figure out a circular shape that would fit this or something like that, that would work. But we just need to approximate. So here's what we're going to do. We're going to divide this space up into 4 little strips. Okay? And I just kind of picked 4 because it was going to work nicely. And what we're going to do is we're going to use a rectangle to approximate the area of each little piece. So let me get my line drawer again. Maybe that's my first rectangle, second rectangle, third rectangle, fourth rectangle. Okay, so we've got an area formula for working with rectangles. Oops, wait, I want that. Don't want that little piece. Don't want that little piece. There we go. All right, so you can see in this first part, the area of that first rectangle is actually really pretty close to the actual area of that little strip. The second rectangle is a little bit off, a little bit further off, but that's okay. It's still relatively close to the area, the actual area of the strip of that space. And then this rectangle, again, a little bit further off. The steeper the curve gets. Ooh, I lost my rectangle. The steeper the curve gets, the worse my rectangle is to approximating the area under the curve. All right, what I've done in each case is I've used the left endpoint of the interval. So I'm looking at, to begin with, I'm looking at the interval. I'll get there in a minute. Interval from 0 to 1/2. And I'm using the left endpoint to get a height for my rectangle. So on the picture, the part that I just kind of highlighted in blue, I plug in x equals 0. That is the left endpoint of that interval. Plug that into f of x. So the height of that rectangle is f of 0, or 1. And the area of that is going to be height, or length, times width. So this is area. The area of that first rectangle is 1/2. So 1/2 is the area of that space. And then I do the same kind of thing for the second rectangle. The second interval from 1/2 to 1. Using the left endpoint, which is 1/2, I find the height. So height is f of 1/2. 1/2 squared is 1/4. Add 1 to that, you've got 5/4. So the area of that rectangle is 5/4 times 1/2, or 5/8. And then my next interval from 1 to 3/2, the endpoint I use is the left endpoint, so that's x equals 1. The height of that rectangle is f of 1, which would be 2. So the area of that rectangle is 2 times 1/2, 1. And then the last interval from 3/2 to 2, using 3/2, you find the height is f of 3/2. 3/2 squared would be 9/4 plus another 4/4. 9 and 4 is 13, so that's 13/4 for the height. So area of that rectangle is height times width, 13/8. So the total area under that curve bad. Okay, slow down. Write carefully. Total area. Okay, the estimate for the area under the curve would be the sum of those four areas. So 1/2 plus 5/8 plus 1 plus 13/8. You do that in your calculator. I certainly wouldn't expect you to add all those fractions by yourselves with no work, although you could do it. Those are pretty easy fractions. That is an estimate for the area under the curve. 15/4 is an estimate for the area trapped under the graph of x squared plus 1 and above the x-axis. Notice that this is an underestimate for the area. The actual area should be a little bit bigger because we're not measuring all of this space that's below the curve but above the rectangles. Now, what we just did using rectangles is called rectangular approximation, and we used the left endpoint. So that's called left-hand rectangular approximation. Which I would refer to as LRAM. RAM is rectangular approximation. L is left. And this is too small. It's an underestimate. Now, could we find the same area or find an approximation for the same area, but instead of using the left endpoint on the intervals, use the right endpoint? Sure. That would be R RAM. All right, so we're still thinking about dividing our space up into little strips. Actually, get that strip, get that one. And then now instead of, okay, that's 1/2, 1/2, 1, 3/2, 2 are my x-intercepts. Instead of using the right endpoint, instead of using the left endpoint to calculate the height, we're going to use the right endpoint to calculate the height. So the first rectangle sticks up just a little bit above the curve. The second rectangle, okay, let's make it a rectangle. There we go. That's better. Again, sticks up just a little bit above the curve. Third rectangle. Okay, includes a little bit more space above the curve. And then finally the last rectangle it's actually a rectangle. All right. So if we calculate the area of these 4 rectangles and add them together, okay, and let me just let me go through and give you those numbers. On the interval, I really hate it when that little pin shows up. The interval from 0 to 1/2. Then we've got an interval from 1/2. If I could write, it would help. 1/2 to 1. We've got an interval from 1 to 3/2. And we've got an interval from 3/2 to 2. Okay, let me move this graph down out of the way a little bit. Okay. Using the right endpoint. Okay, the endpoint, the first row is going to be the endpoint. Come on. Endpoint. Right endpoint would be 1/2, 1, 3/2, and 2. Height. Would be f of 1/2. And you can go back, I'll leave this work for you to do. If you plug in 1/2, you get 5/4. If you plug in 1, you get 2. If you plug in 3/2, you get 13/4. If you plug in 2, you get 5. And then finally, area. Multiply each of those heights by a width. Each interval is 1/2 of a unit long. So your area is 5/8, 1, 13/8, 5/2. So if we sum, if we add those 4 numbers, the total area would be, and this is an estimate, so I really shouldn't write equals. I know I did in the last example, but I shouldn't. Add 5/8, 1, 13/8, and 5/2, and you get 23/4. This, looking at the picture, it's very, very clear this is an overestimate. Okay, the actual area spaced trapped below the curve and above the x-axis should be a number smaller than 23/4. Now, we could also, and I'm not going to actually go through and do that because you can imagine what's going to happen. I'll show you the picture. Instead of, we don't have to use the left endpoint or the right endpoint. What if we used the midpoint of each interval? Okay, so 0, 1/2, 1, 3/2, 2. Okay, thinking about dividing our area up into little strips. What if instead of using the 0 or the 1/2 in the first interval, what if we used the point 1/4 to calculate our area? Or excuse me, to calculate the height. Okay, and I missed just a little bit. Should actually be about right there. Eek. About right there. So, yellow, area of that rectangle. Using the midpoint to calculate the height. Using the midpoint, calculate the height. Using the midpoint to calculate the height. So our rectangles end up looking something like that. Okay, now I kind of think that this estimate, if we actually worked with the numbers here, this estimate we'd get in this case would be a little bit closer to the actual area under the curve. And here's what I'm thinking. This space right here that we're not measuring in our rectangle kind of makes up for this little part of the rectangle that's sticking up above the curve. So when we're using rectangular approximation and we're using the midpoint, we're doing what's called an MRAM, midpoint rectangular approximation. And the midpoint, at least for the example for the function that we've got, that midpoint number, I'll leave all the work to you to do if you choose to. Trust me when I tell you that the total area there, total area of the four rectangles is 37/8. That midpoint number, MRAM, should be, probably closer to the actual area under the curve than either the left endpoint rectangles gave us or the right endpoint rectangles. The left endpoint was too small. The right endpoint gave us numbers that were too big. MRAM is going to be in between there, so it's probably closer to the actual area under the curve. Now, with the example that we've done, with the function x squared plus 1, since x squared plus 1 is just increasing on the interval from 0 to 2, all we care about. These left endpoints that we see right here, we talked about that giving us an underestimate. That's what we're going to refer to as a lower sum. When we used the right endpoint, we got an overestimate. So we're going to call that an upper sum. So when you have rectangles that are circumscribed rectangles, like we see in this picture, the sum of those rectangle areas is going to be an upper sum. It is an overestimate. It's bigger than the actual area under the curve. When you're looking at inscribed rectangles, then the sum of those areas is an underestimate. It's too small, and it's called a lower sum. Now, theoretically, how can we get a better estimate? Well, you could squeeze more rectangles in. Okay, think about it. What if instead of dividing it into 4 rectangles, what if I divided it up into 8 rectangles? So I'm, instead of subintervals from 0 to 1/2, 1/2 to 1, 1 with 3/2, and so on, what if I look at an interval from 0 to 1/4, and then from 1/4, 0 to 1/4 would be there. Oops. 1/4 to 1/2 would be there. 1/2 to 3/4, 3/4 to 1. Okay, so we got twice as many intervals. If you think about, and I'm just to have something to draw, I'm going to draw inscribed rectangles again using the left endpoint of each of my intervals. If you think about calculating the area of each of these rectangles, you can actually see that there's significantly less gaps between the curve and the rectangles. So if you want a better estimate for the area under the curve, you increase the number of rectangles that you squish in there. Now, something that is always going to be true, the lower sum is less than or equal to the actual area under the curve, and the area under the curve is less than or equal to the upper sum. Okay, so L sub S lower sum, U sub S upper sum. So the inscribed rectangles give you an area that is less than or equal to the actual area under the curve. And the circumscribed rectangles give you an area that's greater than the actual area under the curve. Now, let's look at another example. Let's say I have the function f of x equals x squared. And I want to look at that function on the interval from 0 to 2. Okay, so let me get a graph. If I divide the interval from 0 to 2 up into n subintervals, so if we partition, that's the word we're going to use. Partition the interval from 0 to 2 into n subintervals. Here's kind of what we're thinking about. There's 0, There's 2. I'm going to divide this up, and I'm going to divide it up equally. Okay, but let's say I squish in little subintervals. So this is x sub 0. I'll tell you what, I'll start counting at 1. That's x sub 1, the next one is x sub 2, the next one is x sub 3, and so on until we've got x sub n way out there at the end. All right, the interval is 2 units long. If we divide into n equal parts, then the width of that subinterval, the change in x values, will be 2 over n. So if the coordinate of x sub 1 is 0, the coordinate, thinking about a number line, the coordinate of x sub 2 would be 2 over n. And then the coordinate for x sub 3 is going to be 2 over n times 2. Okay, and we can extend that. Somewhere out here we have the ith subinterval, somewhere in the middle. Notice x sub 2 is 2 over n times 1. X sub 3 is 2 over n times 2. So x sub I would be 2 over n times I minus 1. And then the last interval would be 2 over n times n minus 1, and that's going to be equal to 2. So the lower sum would use left endpoints. Because this function y equal x squared has basically the same shape that y equal x squared plus 1 does, and that's what worked before. So the left endpoints are x sub 1. Okay, let me back up and be very, very clear here. The left endpoint of the first interval is x sub 1. The first interval goes from x sub 1 to x sub 2. So the area for that rectangle would be function of x sub 1 times the width of that interval. The area for the second rectangle, x sub 2 is going to be the endpoint that we plug into the function, so that's going to be f of x sub 2 times delta x. The third interval would be f of x sub 3 times delta x until we get all the way out to the nth subinterval. This one very last at the end. The left endpoint is x sub n minus 1. That gets plugged into the function and multiplied by delta x. So what does our function do? Our function squares. So let's see how I can write this. Well, alright, so this is going to be x sub 1 squared times delta x, 2 over n, plus x sub 2 squared times delta x, 2 over n, and so on until we get x sub n minus 1 squared times 2 over n. Now, this is kind of painful, and I realize that. If I'm going to do shorthand notation, I'm going to start from 1 and go to n minus 1. And I've got, let's see, x sub I squared times 2 over n. Well, what did I say the formula for x sub I was? the formula for x sub I is 2 over n times I minus 1. So the sum, if I starts from 1 and goes to n minus 1, I have 2 over n times I minus 1 all squared times 2 over n. Okay, so 2 over n squared is 4 over n squared, and then I minus 1 quantity squared would be I squared minus 2I plus 1, and that gets multiplied by 2 over n. The index in this sum is I. I is what's changing. N is not changing. So the part of that 4 over n squared and 2 over n, I can pull out because it's constant. So I've got 8 over n cubed times the sum, if I goes from 1 to n minus 1, of the quantity I squared minus 2I plus 1. If we break that up into 3 separate sums, 8 over n cubed gets multiplied by the sum from 1 to n minus 1 of I squared minus 2 times the sum if I goes from 1 to n minus 1 of I plus the sum if I goes from 1 to n minus 1 of the constant 1. Using the sum formulas, I squared is n times n plus 1. Excuse me. If we are starting at n minus, if we're stopping at n minus 1, the sum for I squared is the upper limit. Okay, get a pen that will write. The upper limit, so that's in this case n minus 1, times the upper limit plus 1, times 2 times the upper limit plus 1. And that's all divided by 6. Minus 2 times, and our formula for a sum of I is the upper limit times the upper limit plus 1 over 2. And then we'll have just n minus 1 at the end. Now, in the interest of time and sanity, we're not going to go through all the steps to simplify that, but basically we will eventually end up with a formula for the lower sum that is something along the lines of 8/3 minus 40 over 3n minus 104 over 6n squared minus 8 over n cubed. Just trust me on that. If we did similar work to find an upper sum, and again, I am not going to go through all that because we just seriously don't need to do that, but the upper sum that you end up with the upper sum, of course, would use the right endpoints. The upper sum you end up with is 8 over 3 plus 4 over n plus 4 over 3n squared. Now, we talked about the fact that we'd get a better estimate for the area under the curve if we squeeze in more rectangles. So, theoretically, the only way to get exactly the value of the area under the curve is to squeeze in an infinite number of little rectangles. So we're thinking as the number, here's how you have to think about this. As the number of rectangles increases, the lower sum gets closer to the actual area under the curve, and the upper sum gets closer to the actual area under the curve. So as n gets bigger, these two sums we have get closer to each other, and the actual area trapped between the curve and and the x-axis. So we're thinking about the idea of a limit. If you take a limit as n increases, or n approaches infinity, the limits of the upper sum and the lower sum should be equal to each other. Okay, we can see that. If you take a limit as n approaches infinity of that monstrosity we got for the upper sum, 8/3 minus 40 over 3n minus 104 over 6n squared minus 8 over n cubed, all of those fractions that have an n in the denominator are going to 0. That limit is 8/3. Okay, so this is the limit of the lower sum. The limit of the upper sum, okay, which is not as scary to look at, still not very nice, but 3n squared. Those two fractions that have n in the denominator are going to 0, so this limit is 8/3. So this was the limit of the lower sum. This was the limit of the upper sum. You can see that they are the same number. So the actual area under the curve, y equal x squared, on the interval from 0 to 2, is 8 over 3. Now, this is enough to get us thinking the right way. There are actually just a couple of little quick homework problems that you're going to actually try to do from 4.2, because we seriously don't need to go into as much detail, even as what I did here in this recording. But you do need to get the big ideas, that we are dividing our space up into rectangles, and then the way to get the actual area under the curve is to think, take a limit as the number of rectangles approaches infinity. So there's work in Blackboard. There may be a couple of problems in WebAssign. I honestly can't remember right now, so I probably